In this video, I'll provide some more mathematical details about logarithms. In particular, I'll talk about using logarithms to undo exponents and to convert multiplication to addition and subtraction. These properties can be really useful to simplify some engineering analyses. In this video, I'll define logarithms in terms of exponents. If x is equal to a raised to the yth power, then log sub a of x is equal to y. The logarithm simply extracts the exponent from this term, so in some sense it undoes exponentiation. A is called the base of the logarithm. The plot of the logarithm of x looks something like this. The value of the logarithm equals 0 when x equals 1, since any number a raised to the 0th power is 1. A numerical example is that the base 10 logarithm of 10 squared is equal to 2. The base of the logarithm can be any number, but a somewhat special case is if the base is e, the exponential constant. The base e logarithm is denoted as ln, which stands for the natural logarithm. Logarithms and exponentials are, in some sense, inverses of one another. In other words, exponentials and logarithms can be used to undo each other. Taking a logarithm with the appropriate base extracts an exponent, and vice versa. This is a pretty important property, so I want to spend a little more time on it. As before, let's define x as being some number a raised to the yth power. If we take the base a logarithm of x, it returns the power y. Now let's raise the number a to both sides of this equation, which is this. Since a to the yth power is just equal to x, that means that x is equal to a raised to the log base a of x. Raising a to a log base a power of a number returns that number. The exponent simply undoes the logarithm. As an important special case of this is the natural logarithm, where a is equal to the exponential constant. In this case, x is now equal to e to the yth power. Taking the natural log of both sides of the equation gives this. As in the previous derivation, this means that x is equal to e raised to the natural log of x. I'll use this property in an example later in this video. Now I'll talk about three more useful properties of logarithms. The primary one is that the logarithm of a product of two numbers is equal to the sum of the logarithms of the individual numbers. Likewise, the logarithm of a ratio of two numbers, x divided by y, is the logarithm of x, the numerator, minus the logarithm of y, the denominator. Finally, the logarithm of some number x raised to the nth power is n times the logarithm of x. The rest of this video will be examples of applications of the properties of logarithms. Musical scales are almost invariably based on logarithms. Increasing the frequency of a signal by an octave corresponds to a doubling of frequency. So every 8 keys on my piano keyboard corresponds to a doubling of frequency. I'm going to measure frequency here. If I press this key, get a frequency of about 292 Hertz. Going up by an octave, 582 Hertz is about double 292. Another octave, which is equally spaced on the keyboard, is 1173 Hertz. That's double the previous frequency. Let's choose a frequency omega 2 that is 2 times some arbitrary frequency omega 1. If we take the base 2 logarithm of omega 2, that's just equal to the base 2 logarithm of 2 times omega 1. From the first of our properties about logarithms, that's the base 2 logarithm of 2, which is just 1, plus the base 2 logarithm of omega 1. So doubling the frequency increased the log base 2 logarithm by 1. Now let's double omega 2, which is 4 times omega 1. If we take the base 2 log of 4 times omega 1, we get 2 plus the log base 2 of omega 1. Doubling the frequency again increases the base 2 logarithm by 1 again. So factors of 2 on frequency end up as equally spaced points on a logarithmic scale. For example, let's suppose we have some function of frequency. If we use a logarithmic scale on the x-axis, points corresponding to doubling the frequency will be equally spaced on the x-axis. This exactly corresponds to the piano keyboard. If omega 1 was the first key we pressed, 2 times omega 1 was the second key, and it was an octave higher. 4 times omega 1 was the third key, and it was another octave higher. Factors of 2 on frequency are equally spaced on the keyboard. Sound pressure levels are often measured in decibels, which use a logarithmic scale. Decibels are always based on some reference value of pressure called P0. In sound levels, the reference value is the lowest sound level that's typically audible to humans. To convert a sound pressure level to decibels, divide that pressure level by P0, take the base 10 logarithm of that ratio, and multiply that by 20. As an example, the sound pressure level where hearing damage begins is about 85 decibels. The sound level from a jackhammer is about 110 decibels. We want to find the ratio of the actual sound pressures between the jackhammer and the onset of hearing damage. This is the sound pressure level of the jackhammer in decibels, and this is the sound pressure level of hearing damage in decibels. The difference between the two is about 25 dB. By the second property of logarithms, this difference is the same as 20 times the log base 10 of the ratio of this pressure ratio to this pressure ratio. The reference pressures, P0, cancel out, so this is just 20 times the log base 10 of the pressure ratio that we want. Solve for the pressure ratio by dividing by 20, so we get 25 over 20, and taking 10 to that power. That's about 18. So jackhammer pressures are 18 times as high as those that can cause hearing damage. Finally, let's take a look at fitting an exponential function to a set of data. Suppose we've acquired these data points as a function of time and we want to fit an exponential curve to this data. Based on the video on exponential functions, we could use this as our initial point to get y0 and calculate a time constant from the time when we get to 36.8% of this value. However, that relies pretty heavily on this initial point being accurate, and we have no way of knowing whether a single point is accurate or not. It would be better to use all of the data points to perform a least squares curve fit to the data, much in the same way we did curve fitting for straight lines in Chapter 1. If we take the natural logarithm of this equation, we get the equation of a straight line with a y-intercept of the natural log of y0 and a slope of -1 over the time constant. T is this independent variable. Taking the natural logarithm of each of the data points and plotting them results in this. Now we can fit a straight line to this set of data to find the natural log of y0, the y-intercept, and 1 over tau, which is from the slope. Now I have to convert the slope and the y-intercept of a straight line to y0 and tau in this equation. We can get the time constant by inverting this slope. To get the value of y0, we need to undo this natural logarithm. From the previous discussion about exponentials undoing logarithms, we can extract the argument of a logarithm by raising the exponential constant to this value. If I do this with the natural log of y0, I get y0, the initial condition. Extracting tau and y0 in this way results in the exponential function shown here, which fits the data pretty well. Now I'll demonstrate these steps with numerical values. We've acquired these xy data points from a system. They're shown graphically here. We think that an exponential curve is the best way to fit this data, but we only know how to fit linear curves to data. We can linearize this by taking the natural logarithm of these values. So this value is the natural log of this, and so on down the line. If I plot these values, they're shown here, they lie on approximately a straight line. Now, if I fit a curve to these data points, I end up with this as my least squares best fit. The line's shown here, it matches the data fairly well. The equation of the line is -2.54 times x, so the slope is -2.54, plus 0.76. The y-intercept is 0.76. Now I need to undo the linearization process and get back to my exponential curve. The form is e to the 0.76 times e to the minus 2.54x. That turns out to be 2.14 e to the minus 2.54x. If I plot this equation as this blue line over the top of my original data points, I get an extremely good fit to the data. That illustrates several applications of logarithms, but there are a lot more. One feature that most of these applications share is that multiplication and division are transformed to addition and subtraction. This can make rough calculations and preliminary designs a lot easier than otherwise would be the case.